I'm Kenneth Stewart, from a PhD student at the University of California, Irvine, and I'll talk about my work on encoding event-based data with a hybrid-guided SNN variational autoencoder and neuromorphic hardware. So I'll start with the intro and motivation of the work. So as I'm sure we're aware, supervised learning achieves state-of-the-art performance on a variety of tasks, such as the NMNIST digit recognition and DVSGesture recognition tests I show here. However, supervised learning aids labeled data along with many iterations of training. And if you want to learn new classes not found in the dataset it was trained on, you need to do things such as retraining or transfer learning. Additionally, there is difficulty in collecting sufficiently large data sets for supervised learning. So it'd be ideal if we can use the power of supervised learning, but be able to learn from unlabeled data. And there's also limitations of data sets to cover all potential scenarios. For example, if a system is trained to do a gesture such as this swipe down gesture here, and then a user of that system that was trained on that gesture does some variation of the gesture like this, the system may have trouble recognizing it. So it'd be great if we could be able to have a system that can learn this particular user's version of the gesture to customize for their needs on other scenarios. And so one way I've been exploring to accomplish this is looking at variational autoencoders in order to learn a disentangled representation of data such as gesture data to be able to learn from new unlabeled data. And so I'll briefly go over how these variational autoencoders work. So VEs are a type of generative model which deal with models of probability distributions defined over data points X. And these commonly consist of two networks. The first is an encoder network that encodes the captured dependencies of a data sample X, and then encodes this data as a representation in a latent space, which is shown as Z here. And then the distribution of the latent representation Z can be sampled from by the second network, which is the decoder, that decodes the latent representation back into the data space in order to make a reconstruction of the data, which is this X bar here. And the decoder reconstructs this using Gaussian assumptions for the latent space. So neural network classifiers trained using gradient descent are usually overconfident of their classification, making the learning of new classes or variants of existing classes impractical. So an alternative approach is to use the intermediate layers of a trained neural network for pseudo-labels or feature learning for classes. And so to accomplish this, we want to train a variational autoencoder to learn a disentangled representation of the data whose intermediate encoder layers can be used for self-supervised learning by assigning pseudo-labels to unlabeled data. So I do this using a hybrid-guided variational autoencoder. And so here's the hybrid-guided variational autoencoder architecture. And so by hybrid, I mean that the encoder of the network here is a spiking neural network, and the decoder shown here is a non-spiking convolutional neural network. The event-driven map-guided variational autoencoder is trained to generate an embedding that disentangles according to labels in a labeled dataset and that generalizes to new data. The resulting embedding space can then be used for pseudo-labels for supervised learning or for measuring data similarity. The goal of the VAE is to embed the streams of dynamic vision sensor events into a latent space which facilitates the evaluation and data similarity for self-supervised learning from real-world data. And we focus our demonstration of the guided VAE on a dynamic vision sensor, just a learning problem, because of the availability of the event-based DVSGesture Dataset and the high relevance of gesture recognition use cases. And so I'll now go into detail of how each of the components of the hybrid guided VE work. So neuromorphic dynamic vision sensors, or DVS, are inspired by the biological retina and capture temporal pixelized intensity changes as a sparse stream of binary events. This approach has key advantages over traditional RGB cameras, such as faster response times, better temporal resolution, and invariant to static image features like lighting and background. This raw DVS sensor data intrinsically emphasizes the dynamic movements that comprise data such as gestures. And so for our VE, because the decoder is a non-spiking neural network, we use time surfaces shown here as the VE targets for the reconstruction loss. Time surfaces are widely used to pre-process event-based spatiotemporal features and can be constructed by convolving an exponential decay kernel through time in the event stream. This results in two 2D images, one for each polarity, that are used as VE targets for the reconstruction loss. So now I'll talk about the SNN encoder. So recent work has demonstrated how SNNs can be trained end-to-end using gradient descent in backpropagation in time, and along with standard auto differentiation tools, making the integration of SNNs possible as part of modern machine learning and deep learning methods such as VEs. Here we take advantage of this capability by incorporating a convolutional SNN into a variational autoencoder to encode spatiotemporal streams of events recorded by dynamic vision sensors. Additionally, SNNs can bridge computational timescales by extracting slow and relevant factors of variation from the fast event streams recorded by the DVS. And the reason we can train end-to-end a spiking neural network encoder with a non-spiking decoder is that the presynaptic trace of the spiking neural network is equivalent to the reconstructed time surface x star, which is shown here as x star. And the particular neuron model we use for training the SNN is the Loihi integrate and fire neurons. So now we'll go over the what I mean by guided variational autoencoder. So VEs by default do not necessarily disentangle all factors of variation. And to learn a disentangled representation, a supervised guided VE trains latent variables to encode existing ground truth labels while making the rest of the latent variables uncorrelated with that label. The supervised guided VE model targets the generic generative modeling task by using an adversarial excitation and inhibition formulation shown here. This is achieved by minimizing the discriminative loss of the desired latent variable while maximizing the minimal classification error for the rest of the latent variables. And by training these classifiers adversarially and jointly with the VE's encoder, it learns to disentangle the representation. And here the latent variables ZM are the target, are supposed to be learning the target features, and this Z set minus are the latent variables representing any features other than the target features, are meant to be uncorrelated with the label Y star. And we chose a non-spiking conventional decoder for 3 reasons. One, for similarity estimation, we are mainly interested in the latent structure produced by the encoder rather than the generative features of the decoder network. 2, a dedicated neuromorphic processor only requires the encoder to produce the desired latent structure for learning. And 3, an SNN training is compute and memory intensive. And so using a conventional non-spiking decoder enables us to dedicate more resources to an SNN encoder. And we can train the decoder end-to-end with the SNN encoder because the reconstructed time surface is equivalent to the presynaptic trace of the SNN encoder. And so our hybrid guided VAE encodes and disentangles the variations of the structure relevant data, allowing for the clustering of similar patterns, such as similar looking gestures, and the assigning of pseudolabels to novel samples. So we first tried out our architecture on this relatively simple NMNIST dataset, which is the NMNIST dataset recorded with TVS sensor. And so here, the top images are the original digits as time surfaces. And the bottom images are the reconstructed NMNIST digits as time surfaces that are reconstructed by the trained decoder. And as you can see, the original and decoded data are very close in their appearance, showing the success of the training of the VAE to generate the data from the latent space. But we're really interested in the disentanglement of the latent space. And so in order to examine the disentanglement of the learned representations in the latent space, we use a T-SNE embedding to visualize the disentanglement. And so T-SNE embeds both the local and global topology of the latent space into a two-dimensional space for visualization. And so as you can see here, this plot here shows the disentangled latent space as a T-SNE plot, with each digit represented here being clearly disentangled in the latent space because they're in their own cluster. And so now I'll go over the results on the gesture data. And so we used the hybrid guided VAE on the DVSGesture dataset. And so again, here the top images are the original time surfaces of the DVSGesture dataset of the different gesture classes. And the bottom images are reconstructions from the variational auto-encoder of the original data. So as you can see, the reconstructions by the variational auto-encoder are fairly close to the original time surface data of the DVSGesture dataset, showing that the model is successfully trained, the VAE. But again, we're interested mostly in the disentanglement of the latent space rather than the generative features. And so to examine how well the latent space is disentangled, here we'll be looking at some latent space traversals. And so by traversal, I mean that we move along the latent space along different dimensions. And so here at the very top left is a right-hand wave gesture with the latent variable corresponding to the right-hand wave gesture being maximized. And here we also minimize the latent variable corresponding to the left-hand wave gesture. And as we move to the right, here we'll traverse along the dimensions of the right-hand wave gesture over time, minimizing it while maximizing the left-hand wave gesture. And as you can see, as we minimize the right-hand wave gesture and increase the left-hand wave gesture latent variables, the gesture appears to transition to what appears to be more of a left-hand wave gesture. And we also examined the latent traversals of the z-set minus latent variables that are supposed to encode non-target latent variables. And as we move along these dimensions of the latent space, we can see the relative insensitivity to other features that are non-target. And in order to test the generalization of the learned encoder, we evaluate how the VAE model performs when provided with new gesture data captured in a new environment. And so we recorded gestures belonging to two classes not present in the DVSGesture dataset. And these two classes are shown here in this figure as right swipe down and left swipe down. And as you can see in this figure, which is a plot of the latent space of the DVSGesture dataset. And we see that the right swipe down gesture clusters fairly closely to the right hand wave gesture in the latent space, and the left swipe down gesture clusters fairly close to the left hand wave gesture in the latent space. And so we can see that, because these gestures are clustered fairly close together, it shows the capability of the VAE to learn to disentangle representations and classes for new classes and new data. And I also took the hybrid guided VAE and implemented it on the Intel Loihi neuromorphic processor. And so in order to implement this VAE on the Loihi neuromorphic processor, we use Slayer for the pre-training of the network. And so we use Slayer because Slayer has a differentiable functional simulator of the Loihi chip for one-to-one mapping of the trained networks on the hardware. And it uses the same neuron model as quantization as the Intel Loihi neuromorphic processor. And another obstacle with transfer for using the guided VAE on the Loihi is that in the previous network that I was showing, the Z latent variables were trained using a non-spiking network with full precision values. And so in order to put this on the Loihi, which doesn't have those, the mean and variance of the network or the latent space, instead we use the quantized membrane potential of the neuron for the latent representation. And therefore this network can be mapped to the Loihi for inference. And this bottom figure here shows the T-SNE of the latent space for the Slayer membrane potential encoding. And you can see that the representation isn't as clearly disentangled, but it seems to at least be disentangling based on the position of the gestures in space. So here are gestures on the right side of the body. To the left of it are gestures in the middle of the body. And bottom here, gestures on the left side of the body. And so after we transferred the network to the Loihi, we tested the Loihi's encoder inference. And so here's a T-SNE of the latent space representation of 3 gesture classes, the right-hand wave, left-hand wave, and air drums. And you can see these classes are pretty separable in this latent space that's encoded. But if we were to try to embed the latent space with all classes, it would not be clearly separated, which could be due to the low precision integers used for synaptic weights and the membrane potentials. So now I'll go over the conclusion and future work. So in summary, the contributions of this work are: 1, an end-to-end trainable event-based SNNs for processing neuromorphic sensor data, event by event, and embedding them in latent space. 2, a hybrid guided VAE that encodes event-based camera data in a latent space representation of salient features for clustering and pseudo-labeling. And 3, a proof of concept implementation of the hybrid guided VAE on Intel's Loihi neuromorphic research processor. And in future work, we hope to address the limitations of the neuromorphic hardware model and improve the disentanglement of classes so that we can add online learning of unlabeled data with the SNN encoder on the Intel's hardware to create a demonstration of self-supervised online learning. We also want to, in the future, try this method with other types of sensor data, such as EMG data. And I would like to thank Intel for providing me with their hardware and resources, and UCI because that's where I'm doing my PhD, and Accenture for providing funding for my work. If you have any questions, I can take them now.